Now let's do a problem where we have a system of particles. So this is example 4.11 where we have actually two particles A and B, and the problem says the crates A and B of mass m and 2m respectively are connected by a pulley system. So this is of mass m, this is mass 2m. If the system is released from rest, which means that initially the velocity of both A and B would be 0. So let's write that. So given the mass of A, the mass of B, and initial velocity, we'll call this VA1 to be 0 and VB1 to be 0. So we'll say A and B initially are at position 1, and at that instant their speeds are 0. If the system is released from rest and friction between A and the horizontal surface is insufficient to prevent slipping, so there is friction between A and the surface, determine the speed of crate A after B drops a distance h. So after B comes down by a distance h, the question is, what is the speed? So find the speed of A. Okay. Now the question could also ask for velocity of B, and in all likelihood you'll be able to solve for that as well. Okay. So first of all, what is going to pull this down is the gravitational attraction, the weight of B, which will try to pull A in the forward direction, right? Okay. So let's apply our test. Is this a finite displacement problem? Yes, both A and B are moving by certain distances. We have to relate forces with the position, displacement, and the velocity. No acceleration asked for, no time interval here. That means the test is positive. So our step 1 is to choose the coordinate system. So I'm going to fix my coordinate system, right over here, and I will indicate the position of B as YB and the position of A as XA. So let me draw this a little bit bigger. So that's my A, and I have my pulley, which is attached here, another pulley going up, ceiling, and then I have B here. Okay, all right, and A is resting on the surface. So this is where I'm fixing the origin. That's my this is going to be my positive y direction. This is going to be my positive x direction. The position of B is YB, and the position of A is XA. Okay. All right. So we have drawn the coordinate system. We've shown the position variables. Now let's try to do the kinematic analysis. So at this point, you can see that the problem looks very familiar because you've seen something like this in the second module when we talked about kinematics of particles. And clearly there is an inextensible string, which means that the motion of B is related to motion of A, right? So you can clearly see in this case that if B goes up by a certain distance, let's say this goes up by 1 inch, then 1 inch would be released on this side, 1 inch would be released on this side, and then of course the string has to be taut. So 2 inches would be released towards A, right? So which means that there is a definite relationship between the displacement of B and the displacement of Y, and consequently between their velocities and acceleration as well, right? But we will try to do this in a more formal way because we know that the length of the string is constant. So we'll try to write the length of the string as a function of these position variables. So this part of the string from here to here is clearly YB, and this was also YB, minus some constant distance, which we'll ignore. So we get 2YB, plus, then we have XA going in this direction, so that's plus XA, and plus some constant which we don't worry about, and that is equal to constant. So what this is saying is that 2 delta YB is equal to minus delta XA, or 2 velocity of B is equal to minus velocity of A, right? So we are given the displacement of B, which is h, right? So delta YB is given to us, that's equal to h, and that means that delta XA is equal to minus 2 times h, and that's the displacement of A, right? And the negative sign basically reflects that XA is going to be moving towards the right, because this is chosen to be the positive x direction, but A is moving towards negative x, and that sign over here, the negative, is kind of reflecting that. right? So this step is very important because this clearly tells you that velocity of A and velocity of B are not independent of each other. And the kinematic analysis, which is what you learned in module 2, kinematics of particles, allows you to write this relationship. Okay, so let's move to the next step, which is to draw free body diagram. So free body diagram of A. So we'll start with A. A is a particle on the horizontal surface, normal reaction, the weight, and that weight is actually m. Okay, so that's mg simply, and then it's moving towards the right, so there's friction force mu k times n. It's actually mu k n a, and we have the tension in the cable, we'll call that T. Okay, so among all the forces over here, the only forces that will do any work are T and the friction force, right? And A and mg will not do any work because they're pointing in direction perpendicular to displacement. Okay, clearly both the forces are not conservative in nature, so we cannot use conservation of mechanical energy principle, but we can use our general formula which says that the work done by forces is equal to change in kinetic energy. Now let's draw a free body diagram of B. So B has the weight, which is 2mg because 2m is the total mass, and then we have the tension. So there are two T tensions, right? Because there will be tension here. So essentially the tension in this direction is 2T. Okay, now which of these two forces will do any work? Both of them will do work, right? 2mg is going to do work and 2T is going to do some work as well. Okay, now let's try to write the work energy equation for each of them. Okay, so we'll do it for A separately. So work done A is equal to change in kinetic energy of A, right? So what is W sub A? That's the total work done. So that will be T times delta XA. Okay, and T is pointing towards negative direction. Delta X is the other way. So minus T delta XA plus mu K NA, and NA is equal to mg. So I'll just write that times delta XA. So that's the work done by the friction force, and this is positive because the friction force is pointing along positive x direction, and that equal to 1/2 mVA2 square minus 0 because the initial kinetic energy of A is 0, right? So that's one equation that we have over here. Okay, and we can also write a similar equation for B. So the work done on B is equal to the total change in kinetic energy, and we have 2mg. So we have 2mg, and the displacement in the downward direction is delta yb, and both of them are on the pointing the same direction, so that's positive, minus 2t times delta yb equal to 1/2 mvb2 square minus 0, again because initial kinetic energy of B is 0, right? Okay, so we have VA2 here, we have VB2 here. So let's count the number of unknowns that we have here. So we have VA2, VB2. Okay, we have the tension, right? That's another unknown. And delta X and delta YB are completely known because we are given delta YB as H. So delta XA is equal to, from this relationship, minus 2H. So that's known, right? So how many unknowns we have? We have 3 unknowns. We have tension, so let's write them unknowns. We have tension, we have VA, and we have VB. And how many equations we have? We have 1, 2, and we have a third equation, which is the relationship between the velocity. So what this is telling you is that we have enough information to solve for all the unknowns. So you can determine tension, velocity of A, and velocity of B. So one thing to notice in this analysis is to see that we actually wrote the work energy equation for the two particles individually. The question is, could we have applied this for the system, that is A and B together? You could actually have done that for the system, but in general, it is not necessary that the work done due to internal forces would cancel out. So like for example, in this case, you can see that minus T delta XA and minus 2 delta YB are actually equal in magnitude, right? Which means that if you add these two equations together, these two would cancel out, right? you can see that. So delta YB is h. So let's look at this. What is this term? This is minus 2t, delta YB is h. So that's minus 2t times h. On the other hand, this quantity is minus t times delta XA, which is minus 2h. So that's 2t times h, and this is positive. So if you add this with this, they actually cancel out. So in this particular case, it looks like as if you wrote this work energy equation for the system of particles A and B together, the internal forces work actually cancel out. But that is happening in this particular case. That may not necessarily happen all the time. Okay, so it's always preferable to write the work energy equation for the particles individually and then see if the internal forces do any work or not.